Okay, good evening, everybody. Thank you for the opportunity to speak to you again tonight on a topic I think that would interest a lot of you. Since its deployment in outer space, the James Webb Telescope has opened up quite a unique window to the universe, especially for the astronomy community, a window that has never been accessible or available to the astrophysics and astronomy community before. And considering the immense size of the universe, it gives a thrill down your spine to think which other secrets are lying in waiting for us to detect via this telescope. So, as my Scottish friends usually say, these secrets are just lurking in the heather. So, without further ado, one outstanding question in astronomy, astrophysics, is how the first stars and galaxies began to form, and which gave rise eventually to the existence of intelligent human life on Earth, and maybe else in the universe, we don't know yet. The answers, however, lie in the far distant universe. So distant that the light that had to travel for thousands of millions of years to reach us, and with them, they carry the images of the first galaxies and the first stars that formed during that process. So the James Webb Telescope is actually a joint project between NASA, the European Space Agency, and the Canadian Space Agency, to the tune of about $10 billion US, that's $1,000 million. It was launched on the 25th of December, 2021, and was in the early of 2022, it was deployed at what we call the L2 libration point. It's in an orbit around this point. It's located approximately 1.5 million kilometers on the opposite side of the Earth and the Sun, where it can stay outside the harmful radiation of the sun and also escape the heat. So it has a couple of instruments on board, operating predominantly in the infrared region, the near-infrared spectrograph, called NIR spec, the near-infrared camera, MIRI, as a mid-infrared instrument, which is helium refrigerated, and enables the instrument to operate close to minus 225 degrees Celsius. And then there's also an imager and a slitless spectrograph. To compare, let's just compare the Hubble Space Telescope, with which we are all familiar with, and also with now with James Webb. Hubble has got a 2.4 meter telescope lens, mirror. It operates predominantly in the ultraviolet, visible, and close to the nearby infrared region, between 90 and 2,500 nanometers. James Webb, however, operates between 600 and 28,500 nanometer, from the near infrared up to the mid-infrared and the far infrared region. So it operates in a region or a regime that has never been before accessible to the astronomy community. So the main mission is, or goal of James Webb, is to look back in time into the cosmos. Round about this time where the first stars started to form, that is around about 300 million years after the Big Bang. So he searched for first galaxy stars, determine how galaxies evolved from their formation till present, observe the formation of stars from first stages to the formation of planetary systems, physical and chemical properties of planetary systems, including planets in our own solar system from Jupiter outwards, then investigate the potential for life or the existence of biological life in those systems. So it's not surprising that the first focus was on the observing mystery or galaxies. The first formation of galaxies is a fundamental paradigm underpinning modern astrophysics, predicts fewer, and in the process, we expect less massive galaxies in the early cosmic times. However, this is a rare massive galaxy that formed early in the universe, approximately 13.1 billion years ago, and contains roughly, in spite of being such an early galaxy, it contains more than four times the mass of stars than in our own Milky Way. So the results find a massive galaxy in the early universe, 13.1 billion years ago. It's an extremely old population. And this observation upends our current modeling or understanding, as not enough dark matter has built up in sufficient concentration to see the formation. What we observe here is that these galaxies actually form in a region that is very thin in matter. There's very little matter around here, but in spite of that, these massive galaxies have already formed in the early stages of our own universe. So, in spite of just James Webb is not satisfied with just observing the galaxy. They also want to investigate and analyze what is inherently present in this galaxy. So they did a spectrograph analysis from this individual galaxy that existed in a very early universe. And surprisingly, they find oxygen, neon, and of course, hydrogen predominantly. So this data has never before been detected from this far away and at this quality that we see currently with the James Webb. It didn't stop there. James Webb is also interested in exoplanets, and this is an exoplanet called WASP-39. It's a planet unlike anything in our own solar system. It's a Saturn-sized gas planet that orbits a star closer to Mercury than our sun, at a distance very close to this. How can I get rid of this?
Think that arrow on the left of the green strip. That will move it up.
Okay. About 700 light years away from us in the Virgo galaxy. So the upper left no, this is wrong. So this upper left, we see potassium, water, and carbon monoxide. The upper right is around here. Prominent water signal, also around the WASP-39b. The lower left, we see water, sulfur dioxide, carbon dioxide, and also carbon monoxide. And in this lower right picture or spectrograph, we see all the molecules and also including sodium. So this exoplanet is quite extraordinary in its constitution or composition of chemical elements, so almost similar that we find on Earth, but it is so close to the star that these things can't support any form of life. So another interesting exoplanet that was detected and analyzed by James Webb is the K2-118b. Just forget the name. It's 8.6 times more massive than the Earth. It orbits a cool dwarf star in its habitable zone. By means as that is within the a Goldilocks system where they can support water and other forms of habitable conditions, and lies 120 light years from Earth. So it used its infrared imager and found an abundance of methane and carbon dioxide in the atmosphere. And also, very importantly, a molecule called dimethyl sulfide, in short, DMS. On Earth, this molecule is produced by biological processes. So the detection of the methane, the carbon dioxide, and very importantly, a shortage of ammonia are consistent with the presence of water, of a water ocean underneath a hydrogen-rich atmosphere in this exoplanet. So it looks very promising, but there's no proof yet of biological life, although there are signs that biological life could have or can actually develop. Now, one of the main purposes of the James Webb is to look at star formation. What we see here is a protostar detected and imaged by James Webb. The colors themselves, we see blue and also orange, and this is where the star is actually located. The blue areas are where the dust is the thinnest, and the thicker layer of dust, less blue light is able to escape, and therefore creating pockets of orange. So within this Taurus star forming region, the protostar has a protostar, and it has been hidden to telescopes by this dense dark cloud of gas. So the formation has only been made possible or visible in infrared light, and making it an excellent target for the near-infrared camera on board the James Webb Telescope. So the cause of these turbulent conditions, surprisingly only 100,000 years old, which classified itself as almost like an infant in terms of the cosmic history of cosmic. So James Webb also observed stellar structure of a star-forming galaxy called GN20. The UV part here, that is around here, of the blue, is UV emission. Coal dust continuum is the lime, that is the lime part, what we see here. Molecular gas, carbon monoxide, is the orange part, that is around in this area, what we highlight here, and also the purple components of the galaxy, that is these components here. So this star in this galaxy, stars are forming at a rate of approximately 500 solar masses per year, now for a period of 100 million years. And the nucleus, that is the inner part here, is less than 2,600 light years in size. So one of the greatest achievements of the Webb telescope was to observe the pillars of creation. And I've included here a video graph that you can watch. We now compare this area observed by the Hubble telescope in a visible, that is on the left-hand side here. The James Webb in the infrared region, we see much more structure coming out of this image. And then also Chandra, which is an X-ray telescope operating in the X-ray, a very short wavelength in the ultraviolet or the electromagnetic spectrum. We see red dots speckled around here. These are young stars giving off enormous amounts of X-rays. But what is also interesting to note, the scale of these pillars is approximately 4.5 light years in length. It's the same as the distance from Earth or the Sun to the closest star to our solar system, Proxima Centauri. It's just mind-boggling to think of the distances that we observe in the universe, and we're taking sometimes this is as for granted. James Webb also spotted the most distant galaxies ever seen. These are the orange-red objects shown here on this side, and on that, there's a different. It's about 390 million years after the Big Bang. So it occurred approximately 13.8 billion years ago. The light from these objects traveled such large distances as they appear just 350 million to 450 million years after the Big Bang. These observations indicate that the galaxies formed and evolved 100 million years earlier in the universe history. They represent the most distant starlight ever seen before. And these early galaxies had developed well-organized structures. We can see that it's not it's a well-organized structure, almost like a disc shape, out of many stars, rather than being distorted and faint as earlier studies of the Hubble telescope actually indicated. So this is a giant step forward in terms of the knowledge and information that we obtain about the evolution and formation of the universe, enabled only by the infrared observations of the James Webb telescope. I've included this slide just to show you that knowledge is not stationary, particularly not in science. Hubble discovered in 2022 a star that they thought was, and named it Earendel. It formed nearly 900 million years after the universe, after the Big Bang, when the universe was approximately 7% of its current age. This is the image from the James Webb telescope of the massive galaxy cluster, and called the Sunrise Arc. And within that is the star, what they call the most distant. At that stage, they thought it was the most distant. This is where Earendel is located. A closer up view, about 1 million times more luminous than the sun. However, as new knowledge came available and new analysis have been made, this most distant star that was initially thought the most distant star is instead not a single star. It turns out to be a star cluster, a group of stars that are bound together by gravity. It just shows you how quickly things develop in the James Webb observations as they go along. Even what has been observed last week can now be turned around this week and shown that there's more spice to be added to the process. So it's a completely fast evolving paradigm in which we are now operating with. Now, I've included this of the Orion Nebula because I think most of you have already looked at the Orion cluster of stars. This in the upper left corner, shown here, is a young star forming inside a cloud of dust and gas that has collapsed together to form the force of under the force of gravity, giving rise to a new star. This is what we see here. And this is the Orion Ridge that we see here. This is another star forming, wrapped in a cocoon, planet-forming material. And we see the ultraviolet light, strong ultraviolet lights from the trapezium stars in this area eroding the atmosphere around it. Then, in addition to that, we see filaments of hydrocarbon-rich dust and gas that can also be a region where new stars can be formed. So a closer look at this Orion bar reveals the detection of a very important molecule never seen before. It's called methyl cation. The molecule is important because it adds and is formed part of the formation of complex-based carbon-based molecules, which is the foundation that has been used for building intelligence or biological life, or whatever you can call it. It's about 1,350 light years away in the Orion Nebula. So next time you look at the Orion constellation, just think about all the processes that are taking place under our eyes in this area. So the carbon compounds that are now, or that have been formed in this area, are the foundations of all known life. And as such, they are particularly interesting to understand how life developed on Earth and how it could potentially develop elsewhere in our universe. These observations or data has never been possible before James Webb actually appeared on the horizon. So I think Fomalhaut is a star that is well known in the astronomy and also the amateur astronomy community. It's one of the brightest stars in the night. About 16 times brighter than the sun, 440 million years old. But very importantly and very unexpectedly, Fomalhaut was also the host of the first asteroid belt ever seen outside our solar system. And that was made possible by the infrared observations of the James Webb Telescope. It's much more complex, for instance, than the asteroid and Kuiper belts of our own solar system. There are 3 distant belts extending 23 billion kilometers from the star, 150 times the distance of Earth from the sun. The inner belts have never been seen before and were only revealed by Webb for the first time. What is interesting about this phenomenon is that these belts are actually, looks like they can be shaped by gravitational forces produced by unseen planets. But the question now arises, where are the planets? So this is a topic of investigation for more serious and more refined observations in future. The TRAPPIST planetary rocky planetary system created quite a stir a few years ago, and they thought that was one of the systems that could be a topic or a source for the forms of life. 40 light years from Earth, these planets orbit closer to the ultra-cool star than the rocky planets in our own solar system. But on the other hand, the star gives off far less energy than our sun. So Webb's mid-infrared MIRI was put into job and to observe a bit, change the brightness, the planet moved behind its star. So the planet's dayside temperature, however, was found to be close to 230 degrees Celsius. And that eliminated any form of atmosphere or any prospect that biological life could exist in this system. So it did not contain carbon dioxide because that would have been absorbed by light and we would have seen it. So TRAPPIST turned out to be a disappointment in terms of the initial expectations. Webb also finds ethanol in other IC ingredients for making. So the question is, I think you all know what the effect of ethanol is. What do margaritas, vinegar, and ant stings have in common? That is the ethanol-based compounds. So it identified carbon organic molecules surrounding two protostars, IRAS 2A. So these and other molecules detected by Webb represent key ingredients for making potential habitable worlds. Only through ethanol, but I don't think it will last very long in terms of its existence in that area. Very interestingly, Webb also concentrated it and focused on a rare main belt comet called Reed. There's one here at the bottom. Normally, these comets contain water and also, to a certain extent, carbon dioxide. They confirmed the existence of the water vapor, but it did not turn out to have any detectable carbon dioxide, which makes it a very rare type of comet in our solar system. So possibly, one possibility is that Comet Reed did not have carbon dioxide when it formed, but it could also have lost it because of the warm temperatures. We never know, but nevertheless, it made an interesting observation for Webb in the infrared spectrum. James Webb also, one of the key objectives was to look at planets in our own solar system. It contained here the first image of Uranus and its ring system. The atmosphere of Uranus is primarily hydrogen and helium with some methane, which gives it the blue-green appearance. So Webb detected approximately 13 rings around this Uranus planet, which has never been seen before, with clouds on. Then also Jupiter has moons. It put moons in a very new, brand new perspective. Io on the right shows sulfuric volcanic eruptions shown here in the red part of at the polar region. But then also interesting, there's one moon in our solar system called Ganymede. Ganymede is the only planet in our solar system that has got its own internal magnetic field. So it shows for the first time how charged particles are being funneled along Ganymede's magnetic field lines, altering the surface chemistry of the polar caps. These particles hitting the frozen water around the poles and then leading to a process called radiolysis, which then recombine to form H2O2. So a whole new perspective of what is happening in the atmospheres or around two moons in our own solar system. In 1985, the physicist Heinz Hegel wrote that star birth was a veiled and secret event. That's because the stellar crashes hide this action. What we see here is an image of the ESO's new technology telescope. It's a ground-based telescope at La Silla Observatory in Chile, showing the Herbig Haro object called HH4647 and showing jets that emerge from the planet formation. So recently, James Webb couldn't resist the temptation, and they took a look at what happened in the system. There's a pair of forming stars, but we can see a much more detail because from a telescope, it looks completely black. However, when we look at the image from James Webb, a completely new picture emerges. We see two-sided orange lobes, one here and the other one on this side. These are ejections from the star, which appear as blue and blood-threaded features. So the James Webb actually could now observe for the first time how the stars are forming in this region with unprecedented detail that could not be done by ground-based telescope. So what is important is not only the birth of stars, but also the death of stars. This image shows a preview of what is in store for our own sun. This is a view by the near-infrared camera, reveals multiple pairs of outflows shown here, here, and all around from a dying star and pointing in various directions. However, when you turn to the mid-infrared spectrum or instrument, which is another part of the infrared, further longer wavelength, it captures a series of concentric rings around this area. This is actually an evidence that there's a second star lurking around this dying star. The second star orbits the dying star and cuts through the material that's been ejected, as shown in the previous picture. It propagates outwards and carving gaps in this ejected material as it moves away at a distance of approximately 3,000 light years away from our solar system. So this is an image of a shattered star that has already exploded, called Cassiopeia A, an exploded star, one of the brightest radio objects in the sky, which Meerkat has also observed at great length. The star is believed to have exploded approximately 340 years ago. From an Earth perspective, and it's approximately 11,000 light years away from us. So the image shows a shell of material out by the explosion of the interacting gas with the gas, the gas that the giant star actually gave off. The star shattered almost like a glass being thrown onto the ground and then scattered in all kinds of directions. Now, in 1987, a supernova occurred in the Large Magellanic Cloud, which is a sister system of the close to a galaxy close to our own Milky Way. I can vividly remember the occurrence of this supernova. It was quite present and very clearly visible and seen through a telescope and also sometimes by naked eye, 160,000 light years away, first spotted by astronomers 37 years ago. And now with the James Webb, it actually appears that there's something more interesting attached to this supernova remnant. It's a neutron star that's avoided detection for almost 37 years because it was still surrounded by a thick cloud of dust from the supernova. And now we are able to see this neutron star by means of the James Webb. Let me skip this slide and then go to what is called a cosmic mirror. This 10 billion NASA Space Telescope has detected a galaxy that existed just 280 million years after the Big Bang. That is very close to the start of the formation of the of the universe. This is actually called a cosmic mirror, because currently, as the earliest and most distant galaxy ever detected, it's called the mother of all early galaxies, MOMZ14. So this is just an illustration of the redshifted early galaxy. The inset shows the mother of all galaxies. And strangely enough, James Webb also detected a very supermassive black hole powered by quasars in the early universe. What is making this so interesting and extraordinary is that it's an isolated black hole. It's not inside an active or a galaxy as such. It's an isolated black hole. And the question is, how did it gather so much mass to reach supermassive status, especially just a few 100 million years after the Big Bang? So this discovery actually turns everything on its head, what we know about isolated black holes. It grew to an equivalent of to a couple of millions of suns when the universe was less than 1 billion years old. So then something extraordinary must have taken place or is at play or was at play during that time, because these quasars are not necessarily in the highest density regions of the early universe. So this slide might provide a new perspective and an answer to how these massive black holes actually form very quickly or very shortly after the Big Bang. This is the detection of supermassive dark stars that are extremely bright, puffy clouds. They are made up of primarily hydrogen and helium. No nuclear fusion is taking place inside these stars. They are supported against gravitational collapse by minute amounts, and that is what we think, self-annihilating dark matter inside these stars. So this may explain both the existence of unexpectedly bright early galaxies and the origin of the first supermassive black holes, shown here in this view graph. Now, the cat's paw is also an area of massive emission. It's a massive emission nebula, a star-forming region located in the constellation of Scorpius, also known as the Cat's Paw Nebula. It was first detected in 1837 by the astronomer John Herschel on the 7th of June at the Cape of Good Hope. And he is accredited for discovering the cat's paw. The structure is located in the Carina Sagittarius arm of the Milky Way at a distance of approximately 5,500 light years from Earth. So this is now nearing the end of my presentation, and I just want to show what is currently at play.
NASA's James Webb Space Telescope provides this richly detailed infrared view of a massive star-forming region known as the Cat's Paw Nebula. In this relatively small portion of the nebula, Webb explores the star formation activity around the convergence of several dense filaments of dust. This vast cavity is carved out and illuminated by the intense winds and radiation of the massive stars inside it. Peering into these dense knots of dust, infrared light pierces the shroud to reveal deeply embedded stars, seen here as red rubies shining within glowing cocoons. Other massive stars, likely hidden by these dust clouds, shape an even larger bulbous cavern, dubbed the Opera House, that stretches towards the top of the image. After just 3 years in operation, Webb continues to unveil the mysteries of the infrared universe, providing astounding images, groundbreaking insights, and unprecedented scientific discoveries.
So, I want to end off with a quotation by Vera Rubin, who was the first person to show us the existence or verify the existence of dark matter. We have peered into a new world and have seen that it is more mysterious and more complex than we can have imagined. Still more mysteries of the universe remain hidden, awaiting to be discovered. And on that note, thank you very much. Yeah, sure.
I understand when they're talking about stars that composition of the elements they find on it, that's by spectrum they can see that what the composition is. How do they know a protostar is only 100,000 years old or another star is 400 million years old? Do you know how they work that out?
Now, there's a technique, I think they use standard candles in the universe to determine the distances, the age, and also the composition, and what is the mass included.
Yeah, so it is very scientifically worked out.
Yeah, it's actually my pay scale at the moment.
Okay.
So, but there are techniques how to determine those kinds of factors.
How much distortion takes place?
Distortion in terms of the images, or
in terms of the images, yes, because they're using the light that's reflected off the images to determine what the product is.
they use software to clean up all those kinds of, and to a certain extent also artificial intelligence that is used extensively to clean up your, and the image and the colors that you see are actually false colors. They add that afterwards to just to show the contrast of it. This is not how they look in reality. It is added into with software and stuff. So no, you can, but the sharpness of James Webb is beyond recognition. It's much sharper than what has ever been seen before.
Can I share that I've got a book on the James Webb Telescope. I got it from Bargain Books. It's called The Hidden Universe. In other words, it's the universe beyond what we could see before with Hubble. And it's quite expensive. They can order it for you. The entire book is about this thick and about that by that. And it's got an incredible photograph just like this. And basically, it explains the function of each telescope. And it shows you the photograph by each camera. It shows you what the difference is between the two. And as you were saying, they add these colors in artificially afterwards. The technology for this sort of stuff comes from the Cold War, where the Russians were against the Yanks, and the problem they had with the early warning is that how do you know the Russians are going to nuke you? So each side tells each other when they're going to open a silo to be able to launch a rocket. So every now and again, you've got to launch a rocket, just one, to see that everything's working properly. So as long as you do that and you warn the other side what you're going to do, then nobody fires rockets both ways. And so that's exactly what needs to happen. Now, how can you tell from that whether or not the Russians are launching? And so, because the rockets are made of titanium, and the underside of the silo doors are steel, and the top of the silo doors are populated with trees and stuff, deliberately, to make it look like normal ground. When you see the three signatures coming up with titanium, steel, and whatever, okay, so you're picking up the rocket inside, you're picking up the open door, right? But then that is basically the signal. If you see all of the silo doors all opening at once. You know the Russians are going to nuke you. Then you launch all the stuff, first of all, and then let burst. That's basically where the multispectral cameras came from. And they were tested on the moon using the Clementine satellites. The technology was on the Clementine satellites. They couldn't use it on Earth, so they tested it on the moon. And from that, they've been able to get a complete spectrum of all the minerals on the moon by using the Clementine photography. So they did it like a sort of trick, you know. And so they had Russians by the short and curly.
Wow, very.
Very graphic.
Any more questions?
What is the L2 point?
The L2, there are 5 of those points. L2 is where the gravity of the sun and the earth cancels each other. So any satellite that sits there is basically stationary or in a slight elliptical orbit around that point, but it enables the satellite to move along with the earth around its orbit around the sun. The same you get with the L1 libration point is 1.5 million kilometers towards the sun. And a lot of space where the satellites are sitting there looking at the sun 24/7. So they can observe the sun and then see if there are any ejections or disruptions or explosions, and then signal back to Earth. That's a Russian nuke on its way. So this is basically what the L2 point is, just on the opposite side of the sun and the Earth.
L stands for Lagrangian point.
Yes.
But yeah, it's essentially where the solar bodies are cancelling each other's gravity out, creating a zero gravity field at that point. It goes slightly out of it and it moves back up as if it's falling into a well. It's a very stable position for it.
The downside of that is you cannot reach James Webb to make repairs. In terms of Hubble, Hubble is in a orbit, a low Earth orbit around the Earth. So they have made repairs in the past, like adjusting the mirrors. There was some design flaw on it. So they could reach it from the space shuttle and then the space station and then do repairs. But if something goes wrong with James Webb, it's gone. You cannot do anything about it.
The thing that's going to go wrong is the helium in the one camera.
Yes.
So when that dies, then that particular camera won't work, but the others will continue to work because they don't need helium.
They have enough redundancy with all the 5 or 4 instruments to cover almost everything they want to cover.
So could we expect then James Webb to operate for as long as Hubble, possibly?
It could,
in
principle. But there's also cosmic particles that can damage the mirrors.
It's already been done.
Yeah, so they were already done to that. You cannot do it. That's inevitable.
So which mirror has been damaged, Hubble or Webb? Webb already.
Yeah.
It's got a hole in it from a cosmic particle that shot through like a bullet.
It's like a bullet.
So because they come from all different directions,
Yes.
the
Yeah.
shield won't, the Earth won't shield it.
No, it can't. Because these particles don't have their origin on the sun. They have their origin in the universe from supernova explosions. That comes from all kinds of directions.
So it's a bit like an airliner the other day in America. They got hit by a meteorite in the windscreen.
Yes.
Right, and then exploded, and then the
but it
pilot got cuts and stuff, and
right, something like that.
Probably a bit of this Elon Musk satellite.
Whatever.
Any more? All right, I can see you need your mic.
All right, thanks very much, Peter. I think you met the expectations with the extremely interesting topics and so on covered there. And it will, of course, it's been recorded, will be uploaded to YouTube. Anybody wants to look at it again. All right, thanks very much, Peter.
Thank you for your attendance. See you next time.
Bargain book, see if they can get a quiz called Hidden Universe.
I know,
It's about 600 rand.
I'll check that, maybe it's a Christmas. Yeah, thank you very much for that.
Very interesting.
It's a pleasure.